Hi everybody! This is the second part of the tutorial, which explains the basics of a technology called Raymarching for rendering a 3D scene using a shader. In the first part, we modeled a simple scene with a sphere, a cylinder and a cube, and this time we will demonstrate how to properly light such a scene and calculate shadows. So let's get started. So, this is the project as we left it at the end of the previous part. The scene is successfully handled using the Raymarching technique, and now we'll proceed with lighting. So let's start with customizing the camera position, and we'll add a new uniform parameter to do so. I will put it here, uniform vec3, because the camera has coordinates in the 3D space. And let's give it the current value 0, 1, 0. Okay, and we will modify the definition of the ray origin, which is now set to this vector. We will set it to the camera variable. Okay, and let's try it out in the inspector. I will find the parameter, and I think we can move the y coordinate a little bit down. Okay, and maybe the X to this part. Okay, that should be fine. Z to zoom in, zoom out. Very well. Now we need the normal vector at the point when the ray intersects the surface, which is the basis of the correct lighting calculation. So to refer to the sky shader, once again, this was easy for the planet and moon because the normal vector on the surface of the sphere is always equal to the direction from the center of the sphere to the intersection point. However, for other objects like this cube or cylinder, it's more complex and precise calculations would be too complicated, so we'll use a simple approximation. For each ray, we will cast 3 additional rays with a slight deviation from the original intersection point and subtract the result from the original distance, which will serve as a form of simple interpolation. This is basically approximating a so-called gradient, which is usually calculated by partial derivatives, but it would be too complicated and we'll be pretty fine with this approximation. Okay, so let's do it, and I'll start with the deviation vector, which I'll add as a constant. I think we can do it right after the uniform parameters, so that would be const vec2, and I'll call it eps, as the Greek letter epsilon is usually used in mathematics for this kind of small values. 0.01 and 0, that would be fine. Alright, and now the function itself, vec2 apps. Now the function itself, I will insert it right after the Raymarch function, right here. So vector3, call it get normal for the normal vector at the point P, which is the point of intersection. And now, as I said, first we need the distance, normal distance we used before. So as the f of the P point. And so we found the intersection, and now we need the approximate normal vector. Vector3 normal would be distance minus vector3 and vector3, sorry. And the components are the following. Again, SDF P minus eps x, y, y as the fp minus eps yx, y, and finally as the fp minus eps y, y, x. And we need to return the vector, and we are again not interested in the length, just the direction, so we'll normalize that. That would be return normalize the normal vector. Okay. So what I just did here, x, y, 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 x, y, and so on, this is called swizzling, and it is a common technique in the shading language to create vectors from these components in an easy way. So for instance, this is creating a three-dimensional vector with the components x, y, y. And as we know from the app's definition, the x, this part is 0.01, y is 0. So in this function, this means that we are creating a vector 3.0100. This one would be 0.000, this one 0.01. So this is just the standard technique to create the approximation of the normal vector. Now that it's ready, we can proceed with the lighting. So first, let's create a light source as a new uniform parameter. Uniform vector 3, again the coordinates, light source, and let's put it to I don't know, 0, 5, and 7. All right, again we'll be able to change that in the inspector and just move the light source and observe the results. Okay, and now let's create the function getLight right after creating the normal vector here. So func get getLight again with the point vec3 b and vec3 we need the direction, so light there would be, again it's a direction, so we will normalize the vector, and the vector is simply the light source position minus p. Okay, so what exactly is wrong here? Sorry. This is not GD script, of course. Float, not func. All right, and now we need a normal vector to calculate the light. So vec3 normal would be the function get normal of the point P. And finally, to calculate the lighting, we create a dot product between the normal vector and the light direction. And again, we will normalize it. This time, I think we can clamp it to the interval from 0 to 1, like this. Return clamp dot product of normal and light there. And as I said, clamping to the range 0 and 1. Okay, so this is called diffuse lighting, which is based on the angle between the light ray and the normal vector, just like I said. And next, we will use it in the fragment function, where we'll determine the lighting at the intersection point and use this value to set the gray shade of the corresponding pixel, like this. Okay, so here we have the distance as a result of the Raymarch function, and now we need to calculate the lighting, and for that we need the actual point of intersection. So that would be, as we know, the ray origin increased by the length of the ray direction vector, RD times dist. Okay, and we'll use this point as the parameter for calculating the diffuse lighting. So float diffuse is the result of the getLight function on the P point. Very well, and now the color would be simply, instead of distance, we will use the diffuse value. Okay, great. We achieved the rendering of a lit scene. Let's try to change the position of the camera or the light source and observe the results. So, for example, if I put it higher or lower, and I think we could just move to the to the front of the scene, the light, and maybe a bit to the right and more to the top or bottom. Perfect. I think it works fine. Okay, so that's the light. And what about shadows? Their detection is based on a simple principle. We just need to cast a new ray from the intersection of the original light with the surface, this point, towards the light source. If this new ray hits another surface, like this yellow sphere, before reaching the light source, it means that the other surface is blocking the light, and thus the starting point of the new ray is in the shadow. We'll add this algorithm to our code and rewrite the getLight function accordingly. So let's do it. GetLight, here it is. And what we need to do is to create a shadow. So instead of returning this, I will just call it diffuse. Diffuse, and we will finally return diffuse. And now the shadow. So float shadow is, and we need to call the Raymarching to the from the point of intersection to the light source, which would be from P to the in the direction of the light there. Okay. And now let's check if we hit something. So if shadow value is less than the length of the vector from the light source to this point, minus p, so in this case we are in the shadow, so let's dim the light a little bit, I mean the color of the pixel. So the diffuse would be, for example, multiplied by 0.1, which means divided by 10. Okay, and we have already some kind of result, which is a bit unexpected, I guess. It's as if a total solar eclipse occurred in the scene and everything plunged into eternal shadow. The problem is that the ray origin of the shadow detecting ray, the point P, is too close to the surface, as we can see it right here. It's just right there. So, as a result, the Raymarch function immediately detects the condition. I'll show you. Detects the condition. Where is Raymarch? Here. Detects this condition is less than surface dist and ends the cycle. So the solution is to move the ray origin of the new ray a small distance in the direction of the normal vector. To achieve this, we will define one more uniform parameter. Uniform float and call it shadow dist with int range and the initial value 0.01, and let's make it from 0.01 to 1 and the step 0.01. Okay, and let's modify the shadow definition. Where is it? Here. So it is Raymarch p minus shadow dist, I mean light there, and as I said, we will move it a little bit up the normal vector. So I'll add normal vector and multiply it by the shadow dist. Okay, that's much better. And if any unwanted artifacts like this black stripe, or maybe there is some small black dot on the sphere, appear on some objects, we should get rid of it by increasing the shadow dist. Let's tune it in the inspector. So shadow dist. Okay, 0.03 seems to be the perfect value for that. So I'd say that's a pretty decent result. And once again, we can play around with the camera or light settings and observe how the lighting and shadows change. So let's move the camera a little bit and move the light source. Yeah, I'm just moving it forward and backwards, or to the left, to the right, and up or down. Now I put it very close to these objects, so we can see how the lighting is more intense and the shadows are bigger. Perfect. Thank you very much for watching. I can say we have concluded the introduction to Raymarching technology. While we've only covered the very basics, it should still be enough to inspire further experiments. I think that next time we could explore the rendering of different materials and use technology for calculating light refraction and reflection, which will give us very nice results with glass or other translucent objects. For now, take care, best luck with your projects, and I'll see you in the next video.